is we can get by this formula 1/2 A minus A transpose. So in this result is tell that we can express any square matrix uniquely as the sum of skew-symmetric matrix and symmetric matrix, where symmetric matrix is obtained by the equation 1/2 into A plus A transpose, and the skew-symmetric matrix obtained from the equation 1/2 A minus A transpose. So for that, let one example express the matrix A as the sum of square and symmetric and skew-symmetric matrix. For that, the matrix is given: A is equals to 1, 5, 7, minus 1, minus 2, minus 4, 8 to 13. So for first of all, find its transpose. In transpose, we interchange this row by column, and this row is 1, 5, 7 in A transpose, this 1, 5, 7 in the column. In second row, minus 1, minus 2, minus 4 in this A transpose, that is in the column minus 1, minus 2, minus 4. In the third row, 8 to 13 in A transpose, that is 8 to 13 in the column form. So that is the A transpose of the given matrix of A. Now we find the matrix P, symmetric matrix, and that is given from this equation 1/2 A plus A transpose, and we find by 1/2 A, that is given here, plus A transpose. We find in the previous slide A transpose, and final result of that two addition of two matrix, that is 2, 4, 15, 4 minus 4 minus 2, 15 minus 2, 26, and this 1/2 is standing here, and we easily say that this matrix is symmetric matrix because we interchange row into the column. This matrix is unchanged. So the P matrix 1/2, 2, 4, 15, 4 minus 4 minus 2, 15 minus 2, 26 is symmetric matrix. Now find the skew-symmetric matrix. For that, let one equation 1/2 A minus A transpose, and this is A minus this is A transpose, and 1/2 of this, subtract these two matrices, and the resultant matrix is 1, 1, 1 minus 1, 0, 5 minus of minus, that is 6, 7 of minus 8, that is minus 1, and similarly minus 6, 0, minus 6, 1, 6, 0. And we observe that here Q is 1/2, 0, 6, minus 1, minus 6, 0, minus 6, 1, 6, 0 is skew-symmetric matrix. So student can easily verify the given Q matrix is symmetric matrix, because 0, 6, 6, and after interchanging row, that is minus 6, minus 1, that is here minus 1, minus 6, that is 6. So this matrix is skew-symmetric matrix, and write in it into the A is equals to P plus Q form, and the resultant is A is equals to 1/2 2, 4, 15, 4 minus 4 minus 2, 15 minus 2, 26, plus half of into 0, 6 minus 1 minus 6, 0, minus 6, 1, 6, and 0. So matrix A is equals to the sum of two matrices, and the two matrices P plus Q. So the P is symmetric and Q is skew-symmetric. So in this result, we seen that how to express any square matrix into the skew-symmetric matrix and skew-symmetric matrix. Now we define conjugate of a matrices. A matrix obtained from any given matrix A on replacing its elements by a the corresponding ordinary conjugate complex number is called the conjugate of A, and it is denoted by A bar. Means if the, as for example, we have the matrix 1 plus 3i, 8 minus i, 9 minus i, and we note that here that are the complex entry. Means complex entry involve the real part and imaginary part, and the conjugate matrix given A bar by the conjugate of each element, and conjugate of 1 plus 3i element, that is 1 minus 3i, because imaginary part of 3i, and change of this sign is minus 3i, and here the purely real number, means 8 is the purely real number, and conjugate of real number is real number, we know that. And finally minus I, and conjugate of minus I, it is I, and 9 minus I, conjugate of 9 minus I, that is 9 plus I. So this is the conjugate of the matrix A, means A bar is the conjugate of the matrix A, and that is the given from each element, conjugate element, replacing by its original complex number. Okay. Now transpose conjugate of the matrix. In the conjugate of the transpose of a matrix A is called the transpose conjugate or conjugate transpose of a matrix A, and it is denoted by A theta. Sometime we also denote by A star, but we take the notation A theta. Means A theta is equals to A bar of A transpose or A transpose of A bar. That means if we find transpose conjugate, first of all find conjugate and find transpose, otherwise first of all find transpose and after conjugate. As for example, let one matrix A 1 plus 3i, 8 minus I, 9 minus I, and conjugate of that matrix A bar is equals to 3i, replacing minus sign of the imaginary part 3i, minus 3i. This is the real number, so conjugate is real 8. Here minus I, that is the imaginary number, so conjugate of that number is I, and here 9 minus I, and conjugate of that 9 minus I, 9 plus I. So again we let transpose of this conjugate matrix, and that is the given by interchange row and column. Interchange, there is 1 minus 3i, 8 row to the column 1 minus 3i, 8, and I 9 plus I, that is I 9 plus I, and that conjugate of transpose, and that is nothing but transpose conjugate, and that can be denoted by A raised to theta, A theta. Now we define Hermitian matrix. A square matrix A is called Hermitian matrix if A is equals to A theta. Means if we conjugate transpose of that matrix, original matrix A, the matrix A is remain unchanged. For that, as for example, let one A is equals to 1, 2 plus 3i, 3 minus 4i, 2 minus 3i, 0, 2 minus 7i, 3 plus 4i, 2 plus 7i, 2, and transpose conjugate of that element is given 1, 2 plus 3i, 3 minus 4i, 2 minus 3i, 0, 2 minus 7i, 3 plus 4i, 2 plus 7i, and 2. And this transpose conjugate is, observe that, is nothing but the matrix A. So this type of matrix is called Hermitian matrix. Similarly, we define skew here Hermitian matrix. A square matrix is A is called skew Hermitian matrix if A is equals to A minus A theta. As for example, I 2 plus 3i, 2 minus 3i, and 0. If we find its transpose conjugate, the resultant remain unchanged by the minus sign. So this type of matrix is called the skew Hermitian matrix, and student can easily observe that the diagonal element of skew-symmetric matrix must be either imaginary number or zero number, okay, because of this condition A is equals to minus A theta. Discuss one interesting example. Every square matrix can be uniquely expressed as the sum of Hermitian matrix and skew Hermitian matrix. For that, we take one matrix A is equals to P plus Q, means A square matrix A is uniquely expressed as the form of P plus Q, where P is 1/2 A plus A theta and Q is 1/2 A minus A theta, and 1/2 A plus A theta P is Hermitian matrix, and 1/2 A minus A theta Q is the skew symmetric matrix. Means we can express any square matrix into this sum of these two matrix, Hermitian and skew Hermitian matrix. For the verify, let one example: 2 plus 3i, 0 4i, 5i, 8, 1 minus I, minus 3 plus I, and 6. First of all, find transpose conjugate of that matrix, and that is nothing but 2 minus 3i, 5 1 plus I, 0 minus I, minus 3 minus I, minus 4i, 8 and 6, and putting this value into the form P is equals to 1/2 P plus A raised to theta, and that is 1/2 A plus A theta, and the addition of that two matrix is this. So this P matrix is 1/2 4 5 1 plus 5, and similarly this entries, and student can observe easily this P matrix is Hermitian matrix. Similarly, we find Q matrix by this equation 1/2 A minus A theta. So 1/2 into A, write this, minus A raised to theta, and resultant matrix is this form 1/2 6i minus 5 minus 1 plus 3i, and similarly this entries, and easily observe that this matrix is skew Hermitian matrix. So write this combined matrix: A is equals to P plus Q. P is this and Q is this, and this P is symmetric Hermitian matrix, and this Q is skew Hermitian matrix. So in this result we seen that how write any matrix A as the sum of Hermitian and skew Hermitian matrix. Now we discuss about the unitary matrix. A square matrix is called unitary matrix if satisfy this condition: A into A theta is equals to A theta into A is equals to I, identity matrix. I standing for identity matrix. If the matrix A is satisfy this condition, we said that matrix A is unitary matrix. Let one example for that, and first of all find its transposed conjugate, that is A theta. By this A theta is resultant A 1 minus I 1 plus I 1 minus I by 2 minus 1 minus I by 2 1 plus I by 2, and multiply A into A theta, that is A and A theta, and final result of that multiplication we get 1 0 0 1, that is the nothing but 2 by 2 identity matrix. So the given matrix A is satisfy the given condition A theta is equals to I. So the given matrix A is unitary matrix. So we seen this example how verify the given matrix and unitary or not, and also you can find the inverse from that condition, because we get A is unitary matrix. So A theta is equals to I. So write this A into this side, so this becomes A inverse. So A inverse is equals to A theta is equals to 1 minus I, that is the find in the last previous slide. So in this example we see that how to verify the unitary matrix and find the inverse of that matrix. Finally we see in the orthogonal matrix, the square matrix A is said to be orthogonal if A transpose is equals to A transpose A is equals to I. For that, let one example. A is equals to cos phi minus sin phi 0, sin phi cos phi 0, 0, 0, 1. Transpose, let transpose of that matrix is cos phi sin phi 0 and similar that entries, and multiply that A in A transpose. The resultant matrix is identity 3 by 3 matrix. So A transpose is equals to, we get I. So this given matrix A is orthogonal matrix, and from that we find also A inverse is equals to A transpose is equals to that A transpose. So we in this example we see the finally how can find the inverse from the matrix using orthogonal property, and these are the references of the lecture. I hope this lecture is useful to all the students of GTU and other science field. So I stop here. Thank you.